seminar. Today it's my pleasure actually to introduce Professor Hausman, Peter Hausman from the University of California, Berkeley. So he has several caps. I'm going to go over them so that you know the guy. So Professor Hausman is actually the head of the Department of Nuclear Engineering at University of California, Berkeley. He's also the head graduate advisor, the UC Berkeley's radiation safety chair. In 2017, he became, by election, chair of the Nuclear Science User Facility, and I think a lot of you guys are using NSUF facilities, so you know what I'm talking about. Initially, he got his PhD from a university in Australia. I will let you pronounce it.
Montanuniversität Leoben.
Yeah, I can pronounce that. So from Austria in 2008, where he was working on lead bismuth detective corrosion, ion beam irradiations, and microscale mechanical testing were done later on at Los Alamos, where he was a postdoc. And then he joined actually Berkeley in 2010. So that's from 2010 going from assistant professor to head of the department in less than 9 years. That's a good example for all of us here. And in 2014, he won the Best Reviewer of the Journal Nuclear Materials Award, the ANS Literature Award, and in 2015, he won the TMS Early Career Fellow Award, the AIME Robert Lansing Howdy Award. He has authored more than 140 publications, and obviously, today he's going to present just a limited topic of what he deals with usually. So please, let's welcome Peter Hausman.
Well, thank you for this very nice and extensive introduction. I really appreciate that. Well, thanks for having me. It's a great pleasure to be here. I haven't actually been in North Carolina State University yet, so that's a very, very good experience. I saw a lot of things today, and we'll continue to see a lot of things tomorrow, so it's fantastic to see what you got. Yeah, I'm going to talk about some of our research and introduce a little bit what we do. I give it a sort of title, a random title maybe, Synergies and Differences between Displacement and Damage and Helium Effects. Who here took a nuclear materials class? Okay, so not a lot. So who took a materials class? Okay, that's more. All right, good. So it's pretty materials heavy. I mean, materials is what we do, yeah, we'll talk about that. So what I'm going to talk about is a little bit introduction to UCB's nuclear engineering and nuclear materials research efforts, and I have sort of three tasks here. I added actually the first one, which talks a little bit about additive manufacturing. It's a little bit more centered for the nuclear engineers here, who not maybe necessarily all deep material scientists. And the other two topics are really more towards basic material science. Now in the nuclear, so in UC Berkeley we have a nuclear engineering department, which has 9.5 full-time employee faculty, the way we count them, plus numerous very engaged adjunct professors from Lawrence Berkeley Lab and Lawrence Livermore National Lab. And we're trying to cover several, of course, all relevant areas in nuclear engineering, or most relevant areas in nuclear engineering, and have been engaged in anything from detection to fusion, through accelerators to reactor design and what have you. This particular talk, of course, features nuclear materials and, of course, our work on nuclear materials. The nuclear materials and chemistry team is pretty strong at Berkeley. We have two new assistant professors, Lucas Skolek, who used to be at the University of Wisconsin, and Rebecca Abergale, also a chemistry person from previously Lawrence Berkeley National Lab. Now, I'm not going to talk about the chemistry aspects. I'm only going to talk about the materials aspects here. So the nuclear materials efforts Berkeley has actually I'd like to say more extreme environment materials research rather than just nuclear. And so as you can see, we have a lot of nuclear efforts. Most of the efforts, of course, are related to nuclear. But then what you learn from nuclear has a lot of implications to non-nuclear applications. So think of accident-tolerant fuel coatings and claddings. The same coatings and claddings are used for tooling and drill bits and similar things. Silicon carbide is an aircraft material just as much as it's a nuclear material. And so there's a lot of crossover between different fields of applications between nuclear and non-nuclear applications. And in the nuclear world, we of course look at conventional light water reactors as well as advanced reactor materials in some form or fashion. The way I structured the team or the group is in three sort of pillars. We look at mechanical properties, degradation due to radiation mostly, but also environmental and temperature interactions. And then we look at just environmental degradation, which is corrosion in some form or fashion, high temperature corrosion, liquid metal corrosion, molten salt corrosion, gas corrosion, what have you. And then last but not least, fabrication and alloy development. We also were engaged in using additive manufacturing as well as silicon carbide, accident-tolerant fuel development, and coatings. Coatings are always a topic in nuclear as well as many other areas. And most of what I'm going to talk about is actually about mechanical properties, and I have a little bit on the synthesis part on the fabrication methods. And all this work is done by a team of grad students, of course, and postdocs and research scientists who work on these related topics. Yeah, it's not all of it, though. But most of them, anyway. Yeah. Anyway. So let me start first with engineering material selection for nuclear application, the additive part. So if you're a nuclear engineer, or any engineer for that matter, when you have a problem, a car, a reactor, whatever it is, you define your problem. You define what requirements you pose on the material. That may be stiffness, temperature, stress, lifetime, whatever the design criterion is that you may have. And you assign a material's property with this. So if you want to go for stress, and then you go for yield strength. If you go for time, you go for creep, right? And so materials engineers and mechanical folks, they know about Ashby Maps. And Ashby, Mike Ashby came up with this a long time ago, where he maps out property A over property B. It's a database of various properties. And you say, I want to know density over compressive strength or whatever. And you find out low density and high compressive strength. Obviously, you want to be up here. There's no material, so you pick whatever is good here, right? So that's a way of doing material selection. A little bit, rough maybe, but it works actually quite well. Now, if you're a material scientist, then you know a lot of properties are actually tied to the electronic binding of atoms. Plot properties, and there's some relationship. So you find elastic modulus is related to melting temperature because it's all tied to the electronic binding between atoms. Same applies to thermal expansion, right? Melting temperature and thermal expansion, they're related and actually have the same trend. So that's not new to materials people. And you can plot all kinds of materials and you find some sort of trend. Now for nuclear engineers, however, it's a little different because we care about cross-sections. We care about nuclear properties in addition to the electronic properties. And now you add to this the nuclear cross-section, and the size of the sphere represents the nuclear cross-section. I don't know if that was thermal, I guess. Thermal, yeah. Thermal nuclear cross-section. And this trend, which is nice between modulus and melting temperature, kind of goes away once you add the nuclear properties, because they have not very much to do with each other. Now, that, however, makes your material selection rather challenging, because normally you would go, say, mechanical property, chemical, physical, and your common intersection, Venn diagram, whatever is the space in your design, is where you go. If you add nuclear properties, that design space shrinks very, very small. And so that leaves you with maybe 1, 2, 3 materials at the very best. Now, can we somehow overcome this design space? And can we maybe design components which have different properties in different parts of the different regions of your component, of your part? And so we propose, I guess, a novel approach for materials and design of components, which is combining the 3D printing with the materials property. So one can think of it that way, that you have material 1 and material B, and you could maybe just do a dissimilar weld, but you can also grade it, make it continuous. And what that does for you is that instead of designing a component like this one, where you have material A and material B welded together, you design it as a 3D printed component, but you also grade it and have different properties of design with these different materials. And so you could envision things where you have different isotope concentrations in your fuel, where you have different, even isotope concentration, I guess, in your metal part, if you care about that. But you have different magnetic properties, all kinds of different properties. Now, if we do this, multiple materials, or this maybe 4D structures, using 3D printing, laser, in this instance, laser additive manufacturing. And what we do is we change the composition layer by layer. So each layer is a slightly different composition. You grade from material A to material B. And there's, of course, lots of parameters, anything from chemistry to laser parameters and what have you. But we just changed the composition in this instance. So I'm only going to show you one example, what you may learn from this. One example is 316L stainless steel to C300 mar-aging steel. 316L is stainless steel. Mar-aging steel is extremely high-strength material, typically used for tooling and this sort of thing, for wear-resistant components, valve balls, and anything that has friction involved, and you moving parts, right? 316L, on the other hand, of course, is corrosion-resistant and non-magnetic and an austenitic stainless steel and much tougher, but lower strength than the mar-aging steel. So we're going to grade this layer by layer, starting on mar-aging steel and end up with 316. Change the composition by each layer, gets a different powder composition. Turns out that's easier said than done, because you do have to consider phase diagrams to make sure that you're not hitting some weird phases in between. Now, fortunately, there's not too many bad things going on between mar-aging steel and 316. But you do have to consider that these mar-aging steels form a lot of intermetallic precipitates. Stainless steel doesn't. Stainless steel is paramagnetic. This one is ferromagnetic. And the strength is 4 times different. And of course, the thermal expansion is different too. So there's a risk of one ripping the other one apart. And so we make these gradients and then look at them and see if they actually turn out to be gradient, if they are continuously different. So we build these structures and then do an EBSD, electron backscatter diffraction map, which tells us about phase fractions along the length. How much BCC versus how much FCC you get. BCC being the mar-aging steel, FCC the 316. And the blue being the BCC and the red being the FCC crystal structure. And there's, you see that continues, right? When just like, okay, we've changed the composition continuously. And therefore, we would expect that. But then we do a hardness trace along that length and measure the hardness along this transition region. And it turns out that's not continuous. So you would think that the hardness is a continuation between one and the other. But it's not the case at all. So the hardness actually stays the same on the FCC side, pretty good, even though you add some BCC. At some point, however, you've reached one composition where the hardness suddenly jumps. And if you heat treat it right, then it jumps even more. And you get quite substantial mechanical property increase. But it's not continuous. It's a jump from one layer to the next. So we look a little bit deeper in the microstructure and see we find these solidification cells, a little bit porosity in there. Elements segregate to these boundaries and what have you. But nothing too interesting or exciting we see so far that would point to this. Then we etch it chemically, and we see that one side, the hard region, which is the mostly mar-aging side, with the smaller indents, there's no pointer here, I guess, with the smaller indents, that region etches significantly, and the 316 ridge side doesn't, with the softer indents, larger one, does not etch. It goes so far that individual solidification cells, this one etches and the next one doesn't. And so what is it that makes exactly one composition, one layer, etch and the other one doesn't? What makes one 4 times as hard as the now next to each other? So we do transmission electron microscopy, and look at that, and it turns out that, that the hard region, we find a lot of these intermetallic precipitates, which make our material very hard and strong. Now, in the 316 side, that doesn't seem to be the case. We barely see anything like that. And so it seems to be there's one precise composition layer by which you flip over where these precipitates come out, versus in the other instance, at least in normal aging condition, they will not come out. And so when you think that you have a gradient which is continuous and it's a gentle property transition, that's not necessarily given. You may end up with having a very sharp property transition one and another, because it takes one composition, you cross over in the phase diagram to one new phase where this becomes possible versus the other one doesn't. So that's one way of maybe a slightly new way to look at how to make nuclear components, making these 3D grading with changing the composition of it, and make parts. But once we made parts as nuclear engineers or material scientists, we kind of want to Jamal and I, we basically stick everything we have, is stick it in a reactor and an ion beam, and we irradiate it, right? It's kind of what we do as a default. And the question is, what happens then? So when you put some irradiation damage on the material, then you can cause two things. You can cause, obviously, displacement damage. You knock out atoms and displace them from the original lattice site. And that ultimately leads to things like dislocation loops, voids, or some precipitates. Or you may have transmutation or fission or some other reaction which leads to the creation of gases, for particular helium being of interest, which can lead in the plasma to surface changes or blistering of surfaces, but also to helium bubbles within the material. And so for the rest of this talk, I would like to look at displacement damaged materials and helium implanted materials and see maybe what differences and similarities we have. So when we look at the subsequent this damage causes, we find that radiation damage causes dislocation loops, voids, stacking full tetrahedrons, formation of precipitates, maybe grain boundary, elemental changes. But also we can dissolve precipitates, gamma prime and gamma double prime, which is a nickel-based alloy feature, goes away. So you're losing actually strength rather than winning, or you form helium bubbles. Now the way I structure these defects is into defects which can be dissolved due to mechanical interaction. So you deform it and your defects go away, and you deform it and your defects don't go away. So all these defects, dislocation loops, to some degree voids, precipitates, and even, of course, precipitates we dissolve anyway due to radiation. If I mechanically deform them, I can dissolve them, because the mechanical deformation is as dislocations traveling through your material. And if you have dislocation-like features or defects, they can be absorbed in those dislocations. Or we can have features we're not getting dissolved due to mechanical deformation, which will be helium bubbles, precipitates, and it depends on what kind of precipitates we're talking about. And so they have the difference between those two have very different implication if a material turns brittle or not, and how does it brittle under radiation or not, and because its deformation mode changes. And so helium implantation, of course, does this. But displacement damage can do any of those things. And so we look at these differences. Now, when you do an irradiation, we have three ways to irradiate materials, the way I look at it. We can put our material in a reactor, like here, your beautiful reactor you have in the basement. But, of course, the material will be radioactive. That requires hot cells. That requires lots of dangerous work from students. And students get some dose on the film badges and things. Not so desirable. So you kind of want to have your samples very small in order to avoid getting students irradiated too badly. If you can do ion beam radiations. If you want ion beam radiation, that's good too. But you typically have limited beam penetration. You cannot reach very far into the material unless you, again, make your samples radioactive. Or if you're a nuclear chemist, you can have, for example, californium or so, which emits alpha particles of 5 MeV, and they travel about 5 microns into the material as well. Or if you're a molten salt person, the molten salt, of course, implants fission products into the surface of your pipe. And so you get surface implantation due to whatever radioactive liquid your material is exposed to. Now, all of these things have in common that either you have very limited penetration depth of your radiation damage feature, or that you want to keep the volume small because it's a radioactive material. And so you're trying to develop, we're trying to develop small-scale mechanical testing techniques to address the questions I posed earlier on dissolvable defects, non-dissolvable defects, to study these phenomena. And so the other nice thing you can do about small-scale mechanical testing is that if you make your mechanical test samples smaller, and here's like a pillar and a tensile and a compression test, and obviously a tensile test at different length scales, you can test different microstructural features. So if your mechanical test is in the order of a grain boundary, you can figure out what is the strength of a grain boundary before and after radiation. You can test delta ferrite versus regular ferritic martensitic microstructural features in your ferritic martensitic material. Or you can test all kinds of different features you may be interested in and really bridge sort of the length scale from reactor size to the atomic or nano size, if you will, and test whatever you're interested in. And so I want to show you these tests we're doing and developed over the years to flush out the differences between displacement damage and helium damage in the material. So let's look at first as microcompression testings and look at displacement damage. What we typically do is we make these sort of pillar structures. They look a little like from a castle, the top roof features. And then we come with an indenter and compress those things. We did this, so we did an irradiation of 2 MeV protons into a material. 2 MeV protons reach about 20 micrometers deep into the material. And we did 1 dPa and 10 dPa. And mapped out the grain structure. So 20 microns in the material is this deep. And we perform mechanical testing within the ion beam implanted region and outside of the ion beam implanted region. You can put pillars at different distances from that surface. In reality, it looks like this. In the scanning electron microscope pictures, you have pillars here at the surface, some 15 microns deep in the material, and then some beyond 20 microns deep in the material to study in the same grain, irradiated, stopping peak, and unirradiated material. And so when you do this in situ, you can record a movie of the deformation. And so here's my indenter. This is unirradiated. This is irradiated material. And we record a stress strain curve as you do that deformation. There's nothing too exciting in the unirradiated material. It just deforms and just flows. In the irradiated one, I want you to pay attention. There's going to be a white line popping up here and another white line popping out somewhere here, which can be associated with these very distinct large load drops within the stress strain curve. So we're having our stress and strain, and this is unirradiated, irradiated, and stopping peak irradiated. So of course yield strength is a lot higher. But we also observe these very distinct load drops. And so in the unirradiated case, nothing too exciting really happening. But the irradiated case, as I mentioned, there's a white line coming. I don't know if you can see it. There's a sort of a white line coming, and it's getting sort of brighter a little bit. And then there's another one here, which is similar to its neighbor here, right? Same angles. And what happens is all that deformation happens very suddenly within very distinct slip systems. And we see that also in the stress strain curve associated with specific load drops. So we were interested in that. See, what does that mean from a materials perspective? What's going on here? when you plot this out so schematically, we see these load drops, and these load drops are associated with a very sudden deformation, with constant strain rate. So you put these two together, and then suddenly something deforms, and you press really hard, and then you let go, and what's going to happen is you're going to box your neighbor. So that's what the machine does. There's a little bit of a feedback issue. And so you use that artifact actually to mark when a deformation starts and when it ends. And so we do that and calculate the area underneath the force displacement curve, which gives us the energy in that event. And so that we put in correlation with the energy it takes to drive dislocations through this structure. And so we calculate the pile stress, which is the stress it takes to drive a dislocation. The pile stress times the dimension of the pillar plus whatever surface energy term you're going to create. You put the measured energy in correlation to the energy what it should take to drive one dislocation through. That gives you the number of dislocations participating in the event. And then the number of dislocations times the Burgers vector gives you the slip step height. And if you do that, then you come up with numbers. And in this instance, in the unirradiated case, we see all these little tiny slip step heights, very small. And we find that they're somewhere in the order of 50 to 120 nanometers, which is about what they are, according to our SEM image. But if we do this on the irradiated material, we find that for each individual event, we have not just 200 dislocations. We have a few thousand dislocations participating, which is leading to a much bigger slip step height. And so that's what we see here, too. And this is 3 microns. That's about 500-600 nanometers or so deformation. But it all takes place in this one slip band. Why is that? Well, it turns out it's actually well known that particular stainless steels, they form these defect-free channels. So when you deform stainless steel, or in general, any material, it deforms along the Schmidt factors, slip planes, and what have you. But if it's irradiated, you have all these very small defects in there which stop your dislocation motion. But they are dislocation themselves by their very nature, right? They're dislocation loops or stacking fold tetrahedrons, any of that, which is actually the same. It's not the same thing, but it's the same nature of defects. And so the mobile dislocation can absorb these radiation damages, leaving not damaged material behind. And as you do that often enough, you create channels which have actually no defects in them. And so now you have a strong material and a small channel with all the soft stuff in it, and all the deformation is going to happen in the soft region, leading to the fact that you only see deformation in very distinct couple of channels. Now, macroscopically, that would be a very brittle failure, right? Because all your plasticity, all the deformation happens in a nanometer-sized regime, versus normally the entire body would participate in that deformation. And so doing this microscale testing tells us a lot about the deformation mode of these irradiated displacement damaged material are in. The unfortunate thing on compression testing is it doesn't really tell you anything about strain because it doesn't actually fail, right? You squish it, but it doesn't actually break. So that's why we do also tensile testing. And it's not loading for some reason. I think this is not playing. But so we make these T-shaped features and then pull on them and make tensile tests at the same length scale. And we see something very similar, but unirradiated material shows a lot of strain with some very small load drops along the way. And the irradiated material shows a lot of high yield stress, very low strain, and a couple of very distinct load drops, and then they just break. Interestingly, even on a micro scale, these numbers are actually reasonable. So 3 or 4 stainless steel, unirradiated has like 50% or so total elongation. Irradiated, in this instance, got less than 10, which is very similar to what you'd see in a macroscopic test. Now, another interesting thing you can do with these in situ tests, you can actually learn something about the deformation mode itself. So in this instance, we look at the iron chromium alloy. That actually hasn't been radiation damaged, but it's interesting because the deformation mode suddenly changes. This material is a heat exchanger material, alloys. It's a model alloy to alloy 690. And there's a fear that these alloys may form long-range ordered features where chromium and nickel have some ordered structure to them. Think of it as an ordered precipitate. And we don't really we see our deformation the same way we saw it earlier with these slip steps. Most orientations, 111 orientation, 101 orientation, and so on all the orientations except 100. 100, the deformation mode is significantly different than in any other one. And what we see in the movie here is that you see a black band now here developing at some point, and that black band will grow. I don't know if you can see this in this screen here. Oh, there it is, right? So there's a black band here, and it's sort of expanding. There. Now it grew to a size where you can nicely see. Now that's not slipping, that's twinning. The crystal lattice changes by 60 degrees, changes the contrast, and you see that here in the still images too. You actually see the formation of twins, not these slip steps, which is different. So it turns out that if you compress your material in the 100 direction, in contrast to all the other ones, when they have those long-range order features, it changes from slipping to twinning. So which is an entirely different deformation mode, right? They don't have much in common. And the reason for that, as we believe, is that the fact that you have these ordered features. Chromium and nickel want to be or stay ordered when you have precipitates. But in order to shear them, there's only very distinct planes you can actually shear the atoms on top of each other, which don't create an anti-phase boundary where you now have a chromium next to a nickel when it wants to be to a nickel. And if you happen to compress it in 100 direction, you compress in such a way that there's no slip plane which would not cause an anti-phase boundary. If you compress in 10 and 111, then you will not create an anti-phase boundary. And so by doing these in situ things on precipitated structured materials, you can learn something about the deformation mode changing. Another similar example is on alloy 718, which has been now irradiated, and it's well known that 718 forms gamma double prime precipitates, which are the strengthening features. They give us the strength of this material. Well, it turns out that if you radiate these materials, these gamma double prime features go away. They dissolve. You shoot them back in solution. So that's not new. But we can now use ion beam radiation with this small-scale mechanical testing to look at these precipitates getting dissolved or not dissolved. So we do an ion beam radiation into material, similar to earlier, low dose in the front of the peak, somehow at medium dose here, and then unirradiated. And here's again our pillars. And we compress them. And so now we look at in the TEM across this length, and we have the irradiated thing. And we can see these little dots here. Those are the precipitates. And they're much smaller than in the unirradiated region. Unirradiated has pretty large ones, relatively speaking, and the irradiated one has small ones. Where my stopping peak is, I have none. Well, stopping peak has a lot more higher dose than the unirradiated region. And therefore, these large precipitates dissolve more and are completely dissolve at some point. So if you look at our stress strain curves, we would expect from this that our unirradiated material is the strongest because it has the most precipitates. And so indeed, the unirradiated material is actually the strongest. As you irradiate it, your precipitates go away, and so it becomes weaker. Now, interestingly is that the lower dose material, which is edge, shows us these jumps here, very distinct jumps. We lose, they form so fast, again, this example from earlier that we punch our neighbor, versus the peak region actually doesn't have these jumps continuously again. Why is that? Well, if we dissolve them only a little bit, the precipitates become smaller, and we are in the cutting regime of our dislocation. Dislocation is able to cut through it. If they're too large, it will loop around it. And if we don't have any precipitates, well, then there's no resistance anyway, and then it won't cut or loop, and will simply deform homogeneously through our material. So by observing our stress strain curve and understanding our microstructure, we can see when our particles dissolve and when they don't dissolve due to radiation in the material. All right. So those are all sort of micro-mechanical tests we developed over the years, along with many other groups, of course. And we cannot make within the sample in all kinds of different geometries, pillars, dock bones, cantilevers, indentation, what have you, with individual grains. But what's missing today is this connection to the macro scale. How do those small tests really connect to the macro scale? Now, we are really only at the beginning, and the reason, so again, we want to connect to the macro scale, which is a reactor, and we do these sort of tests so far. Now, I'm not going to go into detail about this as an entire separate talk, but one thing, when you do these sort of things, you will learn that there is such a thing as scaling effects. Things don't scale necessarily linear in some form or fashion. It actually turns out that these scaling effects may look something like in various forms or fashions, and therefore it's very difficult to decipher a nanomechanical property to a macro property. The reason this length scale in between is so hard to tackle is because how are you going to make a sample? How are you going to make a sample which is 35 micrometers in diameter? There's not very many methods you can do that with. So it turns out you can do big samples, in this instance, millimeters. You go milling and machining and all that sort of thing. And you can do the nanoscale stuff doing fibbing, right? Focus ion beam machining. In between, there's really only one or two methods you can use. And recently we looked into these femtosecond laser machining tools, which allow us to make 20, 30 micrometer diameter samples, which you can't really make any other way. So about 6 months ago, we purchased from a NEUP infrastructure grant this femtosecond laser ablation tool, and used that to make, for example, pillars. So here's pillars of different length scales, manufactured with our collaborator in Los Alamos National Laboratory, Jonathan Gigax and Stu Malloy. And cutting these pillars with a laser takes minutes, not hours, like on the FIB. The challenge, and so you can very easily make those mesoscale features. Now, it's not as nice as these other pillars I showed you earlier. They're more rough on the edges, and there's probably a little bit more damage from this faster cutting. But the question is, does it matter? Does that damage actually matter? And so Jonathan did ion beam radiation and made these in copper and cut them to different sizes. And if we just make them by FIB, that's the reference, that's the black line, and all those other lines are laser manufactured ones. And the question is, how much material do we have to remove to get to the same mechanical property? So it turns out, if you do just conventional ion beam machining, this is what you get as a flow stress. If you do 10 micron pillars with the laser, and you don't remove, and you cut away to the same dimension as the FIB, you get this much increase. So there's clearly a damage from that laser cutting. And you have to remove about 3 microns or so from the surface to get rid of all that laser damage. But if you do that, then you get the same mechanical properties as that just FIB cut or otherwise manufactured samples. And very recently, we were able to actually make round dock bones in this mesoscale. So this is from about a month ago or two. They're not perfect, but they got a lot better down. So you can see these are like about 40 microns diameter or so, round dock bone samples, which tackle this mesoscale, length scale to help us translate the nanomechanical property to the macromechanical property. This is also a length scale where when you think of maybe having radioactive material, it's not that much material. It's about a human hair is about 25 to 40 microns. So that's about the same diameter. And so now with this laser manufacturing, you can make those geometries relatively easy. There's one benefit lasers provide over any other machining technique. It's non-contact. And you can shoot through glass. So you can machine through a glass window, which means if you're a radioactive sample, all the contaminant stays behind that glass window. So imagine in a hot cell, you shoot the laser through the window, and all the debris stays within a confined environment, and you don't actually have to worry about contamination at all. And so that's a pretty powerful tool now to make any kind of geometry you want without actually contaminating anything. And your tool most certainly not, because your tool is photons. And they basically are for free. So that's nice. And then if you have very ambitious students, they like to use these tools to make fun of their advisor and engrave all kinds of fun things. I'm sure I was not the first one. I'm sure it's a girlfriend of somebody who was first done. All right. So going from displacement damage to some helium effects. And then the displacement damage, I hope I showed you that these purely displacement damaged materials behave brittlely because you can actually dissolve some of those features. Helium bubbles, on the other hand, you don't dissolve. The helium is not going to go away. It stays in the material. So I'll show you some cool techniques we developed to study helium bubbles in materials. A few years ago, we won an NSF MRI where we purchased a gallium, neon, and helium multi-ion beam microscope. And it's really meant for imaging. It's meant for using helium and neon ions for imaging, not necessarily for anything else. It's a bio thing. At the time, I was very interested in bio thing. Anyway, but we actually kind of misuse it and use it as a nano accelerator. And so we have a 0.6 nanometer beam of helium ions we can raster across surfaces. And so you do, we implant 5 by 5 or 10 by 10 micron fields in our material and get some dose in there, and then do nano-indentation, atomic force microscopy, TEM lift-outs, everything you want to know about helium implantations. And just to give you an idea, to do 3 of these different doses takes you about an hour and a half or so. It's very quick because your current is relatively high, but you're only implanting a very small region. But none of those materials, characterization tools, need a lot of material. You don't need much flash for this. You don't need big samples. You can do with very little samples for any of these techniques. And so we use that to implant. Now, what happens if you blow helium in materials? It swells, right? So we blow helium into a surface, in this instance copper, and where we blew it in, the material increases in its height. And that's an AFM image. Bright means high, dark means low. And so we see is more and more dose, 7.5 times to the 10 to the 17 ions per square centimeter implantation dose, and 18 and so on. At 18 in copper, we see these nubbles coming up. And it turns out these nubbles look something like that. Interestingly, they have these black X-shaped things, which I'm going to come back to later. And so you measure the height increase as a function of dose and get your swelling parameter out of that within about 3 hours worth of work. Now in the transmission electron microscope, that takes a lot longer. You see, of course, your helium implants, the helium bubbles in your material. Interestingly, the helium bubbles, they're not random. They have some sort of structure to them. If you take that image and you calculate a fast Fourier transformation from that image, you find there are peaks. Those peaks say there's an order to those helium bubbles. Called that helium bubble superlattice. It was found in the 70s and 80s. If you do a higher dose implantation, your bubbles get a lot bigger, not surprisingly. And so now we can measure the bubble density and calculate the swelling derived from the images. And when we compare the TEM samples to the AFM samples, we find by TEM, by the image, we should see 97 nanometer swelling. The AFM tells us 91 nanometers. This dose tells us the TEM 39, and the AFM says 33. Pretty good match. Means we don't lose much to sputtering or some other artifact. And so we can plot swelling as a function of dose on different materials within a few hours worth of work. One question is, what is the pressure in these bubbles? That's a relevant question because that tells you how much helium can be accommodated in them, and is there any strain associated with them. So when you assume van der Waals gas laws and typical pressure and surface tension equations, you can calculate that when you implanted 5 times 10 to the 17 ions per square centimeter, the bubbles are large enough and many enough that you can accommodate 2.3 times 10 to the 18 heliums per square centimeter. So your bubbles are much larger than they need to be. which means the bubbles are not in equilibrium pressure, they're below equilibrium pressure. And the same is true for higher doses, even so the factor between the two is actually much higher, it's even factor 7. So our bubbles are under-pressurized. Well, why would that be? Now, one thing, when we implant ions into a surface, we don't just put the ions in there, we also create a lot of vacancies and interstitials at the same time. Now, if you already created a seed for a bubble and some helium, now the vacancies are going to join that. In the 1 times 10 to the 18 ions per square centimeter, that's a dose of 40 dPa, which is, of course, quite high. And so it's not just the bubbles themselves, but it's also the vacancies joining those bubbles at these incredible high dPa rates, 40 dPa within an hour, is quite significant. And so these bubbles tend to be not in equilibrium pressure. If you do nano-indentation on those, we see that the elastic modulus actually goes down with those. Why is that? Well, if you form more and more bubbles, it's a composite. It's not dense material anymore. It's a foam eventually. Remember that picture with lots of holes in it? Well, it's a foam. And so the elastic overall property goes down because of this foam property. In the hardness, however, it's a little different. The hardness first goes up and then goes down with those. Well, why is that? If the bubble is very small, it's an obstacle for dislocation motion, and therefore it hardens the material. If the bubble becomes too big, the foam character starts dominating. And for that volume you're testing, it actually is much less because you have a lot less copper in the same volume because most of it is bubbles at that point. So then the hardness comes back down again. Same reason, I guess, the elastic modulus go down. But initially you have a hardening. And I pointed out earlier that we see 10 to the 18 or so, we see these blisters here on the surface. We see these X formations. And we see, actually, if you look carefully here, also sort of a cross in between. Now, those look very much like slip steps. And since this is copper, and the shear planes is 1, 1, 1. So this is on the 1, 1, 1 planes. We see the formation of these blisters developing. Interestingly, the black lines we think is actually ion channeling, because when you shoot the ions in at specific crystallographic directions, the ion travels steeper in the material than it would in others. And so when the ion travels steeper, since image you're creating is a secondary electron picture image, you have less signal to your detector, therefore it's dark. And so if you happen to hit the channeling axes, then you get a black line. And so fortunately, Gerhard Hobler and Kai Nordlund calculated channeling directions for copper in various ways. And you find that in 101 and 011 and so on, they find very strong channeling, and along these lines to these different directions, there's strong channeling. And it seems that they match pretty well with our blister, which pops out and then actually shows these channeling contrasts. And then similar to what we had earlier with the displacement damaged material, we can also implant pillars in our material. So we make, again, pillars as just before, and then implant those with different doses.